Welcome to the latest HACC Tech Talk, and this is the second talk in our Summer 2024 series. My name is Naveen Purushottam from the AMD University program, and I'm very pleased to be able to welcome our two speakers for today. Before I do that, I'd like to briefly introduce our HACC program and this series of talks for anyone new to the program or these sessions. The HACC Tech Talks are intended to highlight some of the applications and research related to the Heterogeneous Accelerated Compute Clusters program. The program is a special initiative from AMD to support novel research in heterogeneous accelerated computing. HACC centers have been set up at partner universities around the world, and our newest HACC is at IISc, the Indian Institute of Science at Bangalore. Each HACC consists of compute nodes enabled with AMD EPYC, Alveo, Instinct, and Versal computing hardware. Participants in the HACC program can access these nodes remotely for their own research. And if you're a researcher working in high-end compute and related fields, we invite you to join the program. You can find the details of the web page shown on the screen. So today, there's a little change. Our first speaker is going to be Dr. Linghao Song, and he's a postdoctoral researcher in UCLA Computer Science Department, and his research interests include machine learning acceleration, computer architecture, and deep learning applications. He will present on two FPGA-based HBM accelerators for enhanced computational efficiency. And these are Serpens and Callipepla. And I'll just say that please post any questions in the Q&A, and we'll try to address those at the end of each presentation. And if you would like to discuss something in more detail, I'll refer you to the HACC program user community, where you can also connect with the speakers. So over to you, Linghao.
So hello, I'm Linghao Song. I'm a postdoc from UCLA. So today I'm very happy to introduce our works on sparse linear algebra acceleration with high bandwidth memory FPGAs. So this talk will cover our latest works, include Sextans, Serpens, and Callipepla, these three HBM FPGA accelerators. So our accelerators target the sparse matrix multiply SpMV and sparse matrix vector multiply SpMV. So the SpMV and SpMV can be represented in C equal to alpha A multiply B plus beta C. So in this equation, A is a sparse matrix, B, C are two dense matrices or vectors, and alpha and beta are two constant scalars. So we do SpMV and SpMV accelerators because they are widely used in many applications like sparse deep learning, graph convolutional networks, graph analytics, and scientific application. And more importantly, almost all real-world large-scale applications use sparse data, and this SpMV, SpMV, and sparse linear algebra are the fundamental operators. So because we will build FPGA accelerators for deployment for computing. However, here are a challenge we are facing with. So we know that FPGAs are good for accelerator architecture prototyping, but when it comes to the performance, we know that in a classical performance model, so the peak performance is the inverse of execution time, so which will be proportional to the frequency. So let me show you some typical frequency of computing devices from CPUs, GPUs, ASICs to FPGAs. So here we can see that among the four platforms, that FPGAs has the lowest frequencies. So is that always true that low frequency will give you low performance? So in fact, we have the opportunities. So to model the performance, we actually have a model called roofline model. So in the roofline model, there are three components. So besides the peak performance, we have two other components, which is bandwidth, that is related to memory resistance, and the computational intensity, which is related to the application itself. So there are two categories of applications, typical applications in the ROOFLab model. So one is the computation bound application. So for example, suppose we have a platform which has a bandwidth of 10 GB per second, and the max performance is 200 GOPS per second. And we have 100 processing unit, and the computational intensity is 40 ops per byte. So to achieve this high performance at this EX1 point, we actually need 2 GHz frequency to saturate this 200 GOPS max performance. So another example is the memory bound application. So we assume the same, platform configurations. The only difference is the computational intensity. Now it's 1 ops per byte, from 40 to 1 ops. So now our focus are moving from this point to this point. So now for this point, it's memory bound. So what you need to do is that you only need to saturate this memory bandwidth. Now to saturate this memory bandwidth, the required frequency is relatively low. It's only 0.1 GHz. So here comes our opportunity. We have FPGAs, which usually works in a relatively low frequency. And we need to focus on the memory bound application, that is sparse workload. So here, give you an example. Compare the two applications. One is the ResNet 50, which is computation bound. The computational intensity is very high, like 20 flops per byte. And for the SpMV, which is memory bound, the computational intensity is low, less than 1 flop per byte. And we need platforms which has high memory bandwidth, because our application is memory bound, so we need the high memory bandwidth to achieve a high performance. And very fortunately, the latest Linux FPGAs actually provide this HBM, like the U280 and the U55C. So this is very perfect for us to build. So now our architecture goal is to, from the previous, to focus on how to achieve a very high computational intensity. Now our goal is how to saturate the memory bandwidth. So another question probably you will ask is that how low should we set our frequency to be? So since we need to match our memory bandwidth, the matching frequency can be calculated by actually the bandwidth divided by the maximal data width. So for the widest platforms, this data width is 512 bit, and the memory bandwidth provided by the U280 FPGA is 460 GB per second, and it has 32 memory channels. So we can calculate that the required frequency is actually 225 megahertz. So we know that this frequency can be very easily be achieved by the current FPGA tools. So let's talk about the challenges in the sparse processing. So in the sparse processing, the first challenge we are facing with is the random off-chip memory access. Because we are processing large-scale matrices that are stored in off-chip memory. So here in this example, suppose we first compute the green 2 element. So we need to read this green 2 element from this sparse A matrix, and then we need to read the corresponding B columns and then do accumulation on this C row. So suppose next cycle we move to the process of this light blue 5 element. Again, we need to read this element from the A matrix, and then we need to fetch this column from the B matrix and then do accumulation on this row or C matrix. So here we see that all the memory access to the 3 matrices, the A, B, and C, are random. And we know that random access and the off-chip memory access is very expensive. So how can we solve this inefficiency of the memory access? So our scheme is that we partition these 3 matrices, the A, B, and C matrices. In the processing, we first read in a block of B matrix from the off-chip memory to the on-chip. And then we stream in the A matrices And every time when we stream in one AIM element, we do the random access on chip. So in this way, you can see that all the random access now happen to the on-chip memory, which is very fast. And for the off-chip memory access, we do the sequential and streaming, so which is also very efficient. Those next challenge we are facing with is about the floating point operations, and that's the floating point operation usually introduce pipeline bubbles to our computation pipelines. So we know that floating point cannot be complete within one cycle. So here I assume that one floating point accumulation is 2 cycles. So in this pipe, in the accumulation pipelines, there are bubbles between any 2 element accumulations. So we know that bubbles is not efficient for the pipeline. So how can we reduce some of the bubbles in the pipeline? So our scheme is that we just do not follow the default orders, but we use an out order scheduling. So this idea is that we can move a later element that do not have a conflict with some element in your pipeline from some later cycles to cycles like here. And in this way, we can utilize most of the bubbles in the previous pipeline. And next challenge is about the how can we support arbitrary problems, because we like to deploy our accelerators in cloud for computing. So that means we do not want to, generate a new hardware for new problems. So by default, with the fixed size hardware accelerators, you can, decompose our large scale problems into small pieces and then launch the kernels from the host side on the fixed accelerators multiple times. But that will increase the high, host to accelerator latency, because you need to launch the kernels from the host CPU, and this launch signal will go through the PCIe to the accelerators, and then you need to wait the failure signal from the accelerators back to the host CPU. So we know that the PCIe latency is usually around 0.1 to 0.2 millisecond. So if you are running over large scale problems, so that means you will need to launch the kernels many times. This host accelerated latency will accumulate to a very high overall processing latency to your processing time. So to alleviate this host accelerator latency, our scheme is that we do not launch the accelerators from the host CPU. Instead, we move the launching process to the accelerator side. So our idea is that we deploy a controller here at the FPGA accelerators, and then we use instructions to control the processing of the processing engines for different problems, different problem blocks. So in this way, we can save a lot of the launching process time. So here as a comparison, when we put the launching process to the accelerator side, now our control latency is very low. Usually it's within a few cycles, that is less than 10 nanoseconds. So here we can see we get a speed of 10,000 times for the control. So after discussing the challenges on designing the accelerators, here let me show you the overall architecture of our accelerators. So our accelerator is a hierarchical architecture which has 3 hierarchies. The first one is the processing engine group, which is responsible for the matrix block computation. And the second level is the processing engine, which is for the scale vector computation. And the third level is the processing unit, which is for the scalar computation. And our architecture is memory centric, so which means we can scale our accelerators to match the different memory requirements. And we prototype our accelerators with the HLS, high level synthesis. And what we do is that we first use HLS C++ to describe our accelerator architectures. And then we use the whitest tools to transform the C++ code to the hardwares. So for the SPMM accelerators, so it takes 10 hours and from the architecture description to the bit stream. And for the SPMV accelerators, it takes 6 hours. So it's very fast. And we actually open sourced our both the bit stream and the architecture description C++ or our accelerators on the GitHubs. So that means it can be very easy to reproduce our works. For the performance, for the SPMM performance, we compare the performance of our SPMM accelerator with the K80 GPU. So we compare with K80 GPU because the K80 GPU and the platforms, the FPGA platforms we are using, the U280, they have the very similar memory bandwidth. So for the peak throughput, our accelerator achieves 1.5x times than the GPU. And for the energy efficiency, we also get 6 times more energy efficient than the GPU. And for the NND, so which is the number of non-zeros, we can support up to 150 millions. So for the SPMA performance, we first compare to K80 GPU, and we achieve 2 times speed up and 6 times energy efficiency than a K80 GPU. We also compare with 2 other, FPGA accelerators, the Warp-Lily and the high sparse. So notice that these 3 accelerators are prototyped on the same FPGA, the U280 FPGA, and we achieve the 2 to 3 times speed up than the Warp-Lily and high sparse accelerators. And we also achieve 1.71x energy efficiency than the Warp-Lily accelerator. So after building this kernels for the SPMM and SPMV, we are thinking about integrate our FPGA accelerators into real-world applications. So here, our target application is the ANSYS LSD, because ANSYS LSD is a simulation software for modeling and engineering problems, which is widely used by many companies and also those industry companies. So the ANSYS LSD can use for many applications like car crash, the modeling of car crash, fluid dynamics, and also some material analysis. So our work starts with the analysis of the performance bottleneck of ANSYS LSD. So first profiling and end-to-end execution ANSYS LSD on CPU, and then we found that the conjugate solver is a bottleneck. So for this, the end-to-end execution, all time is around 700 seconds, and the conjugate solver actually takes 94% of the overall time. So that means it's a very perfect application for acceleration on HBM platform, because there are 2 reasons. The first one is that there's only one bottleneck that dominates the overall process time. So if you have multiple bottlenecks, that means you need to design multiple accelerators. But very fortunately, we only have one single bottleneck, that's the conjugate solver. And second reason is that the bottleneck, the conjugate solver is memory bound. So that means it's perfect for the HBM FPGA acceleration platform. So the conjugate solver used in the ANSYS LSD is a Jacobi preconditioned conjugate solver. So the algorithm actually looks like this. So this algorithm literally solves AX equal to B, this equation where A and B are known and X is unknown. So this solve process is actually an inverse operation of SpMV. And this JPCG algorithm iteratively finds errors and approach a solution. So in this algorithm, SpMV and vector-related operations are the main operators. So to map the JPCG hours to the hardware accelerators, what we first do is that we first build computation modules for all the SpMV and vector-related modules on our servers, on our hardwares. And next, we deploy the memory modules. So these memory modules are used for read and write from or to the HBM memories. And next, we need to deploy the control modules, which is used for the coordination of data flows. So, and we also deploy a global controller to control the overall execution of the accelerators. So we call our accelerator architecture Callipepla. So here you see that there are so many, hardware components and variables. So the problem is that how can we coordinate the computation and data flows in such a complex system? So our scheme is that we come up with a string-centric instruction set. You solve the complex control and the data flow coordination. So there are three types of instructions in our stream-centric instruction set architecture. The first one is the vector control instruction, which is used to control the vector flows between the modules and computation modules. To use the vector control instructions, you need to first tell whether it's read or write operations. So actually, we can support simultaneously read and write. And the next, you need to tell the base address of the vector and the length of the vectors. And the final thing you need to do is to tell the QID, because one vector can be, connect to different, computation modules. So you need to use this QID to tell the destination modules that will send this vector flows to. So the next, the type 2 is the computation instructions, which is used to invoke the execution of computation modules. So to use the computation instructions, so you need to first tell the length of the vectors. And here, we also use a constant alpha. So because in the JPCG servers, it need to do the scalar to vector operations. And the last one is the QID. So similar, this QID is used to tell the destination module index. And the third type is the memory instructions. So this instruction, memory instruction is used to read and write vectors from or to the HBM channels. So to use the memory instructions, you need to tell whether it's read or write operations and the base address and the length of the vectors. So here, let me show you the process of our string-centric instruction set architecture. So there's a global controller, which is used to issue the computation instructions and the vector control instructions to computation modules and the vector control modules. And the vector control modules will issue the memory instructions to the memory modules. And then the vector control module will coordinate the data flows among all the on-chip modules. So with our string-centric instruction set architectures, the global controller code will be very efficient and effective. So here you can see, to use our string-centric instruction set to do the X vector update. So what we need to do is that we first need to issue a X vector control instruction. And next, we need to issue another vector control instructions about the vector P, because in this operation, it involves the two vectors, the X the X vector and the P vector. And next, we need to issue a computation instructions to the X update modules. And finally, we need to actually wait the response from the X modules because we need to keep the memory consistency. So to evaluate our JPCG solver, we compare with three different platforms. The first one is the SCG solver, which is a JPCG solver provided by Vitis. And the second one, Callipepla, is our accelerators. And the third one is the NVIDIA A100 GPU. So for the overall throughput, so we see that actually the A100 is the highest, because if you compare the bandwidth, the A100 has the almost 5 times of the memory bandwidth compared with the two other FPGA accelerators. But actually for a bandwidth of 1/5 of the A100 bandwidth, we still achieve like 75% of the peak performance compared to the A100 GPU. So for the fractional P, which is the matrix to evaluate the computational resource utilization. So for the A100 GPU, we see that it's less than 1%. So that means you buy a very expensive GPU, but you only use like less than 1% of the overall computation resources. But for our accelerator, we achieve 10% of the fractional P. And for the energy efficiency, actually we are the best. We are almost 3 times, more energy efficient than the GPU. After evaluate the JPCG solver itself, we also integrate the JPCG solver to the ancestral software to provide an end-to-end execution of the ancestral software. So we evaluate on this this input, which is a UK atomic weapons establishment benchmark, and we evaluate on 4 platforms. For P1, which is a baseline, it has 1 Intel Skylake CPU with AVX 512 instructions. And the P2 is a platform with 8 MPI ranks or Intel CPUs, and the P3 is a platform with 1 NVIDIA A100 GPU, and the P4 are our accelerators. So here you can see for the performance, actually, to compare with the P1 platform, which is a 1 CPU with AVX 512 instruction, we achieve 9 times speed up. And even compare with the platform P2, it is a platform with 8 MPI ranks of CPUs. Our FPGA accelerator still achieve speed up, but we are slightly slower than the GPU platform, because you know that the GPU has the highest bandwidth. On the right-hand side, I show you the terminal output of the ancestral execution. So here it says that the U280 FPGA is used for the computation. So that's all of my talk. So in this slide, I would like to thank my collaborators and funding agencies. And these are the 3 papers covered in this talk. And we also, open source all the source code for these 3 accelerators. So you are welcome to find our source code on GitHub and reproduce our works. So thanks for your listening. I'm happy to take questions.